So today we're very happy to have Oscar Varela, who will tell us about Kaluza-Klein Spectroscopy from exceptional field theory.
Thank you, Juan, and thanks for the opportunity to present this talk here. This is work I've done over the last few years with my students, Sarah and Gabriel, and the idea is to go back to revisit some spectroscopy analysis that people started doing, I suppose, back in the 80s, and there's been very little progress associated to that ever since. I review a few things why that is the case, and then I'll introduce some new techniques that help us make progress on that front, at least with some assumptions. And perhaps the main idea is that the spectral analysis that can be done in certain supergravities in lower dimensions can be extrapolated to higher dimensions. That's essentially the bottom line. For that reason, I'll review the problem in those lower dimensions, and then I'll extrapolate to the full spectra in the high dimensions, with going through specific examples, and then I'll conclude with some extensions. So of course, the motivation to revisit the old Kaluza-Klein spectral problem is, at least the solutions with anti-de Sitter factors, is related to the anti-de Sitter conformal field theory correspondence, because the key entries in the holographic dictionary relates the spectrum of single trace operators of the dual conformal field theories to precisely the spectrum of Kaluza-Klein excitations above the corresponding anti-de Sitter gravity duals. That problem is not an easy calculational problem, because it involves a number of hot steps, even for the simplest type of round-robin type solutions. The main four steps that are needed in what I'll refer to as the standard analysis is to get rid of gauge redundancies by some perhaps complicated field redefinitions. Of course, you need to linearize the equations of motion, because we're dealing with excitations, with perturbations. Particularly tricky is this expansion in harmonics that involves scalars, spinors, and vectors of the internal compactification space. And finally, if you reach that stage, you just are typically left with a diagonalisation problem of certain mass matrices. This is this is how the problem looks for the a spectral problem type 2e on ADS5 times S5. So it's a bunch of complicated equations that can nevertheless be solved. And Kim Romans Nieuwenhuizen famously did that and compute the spectrum of vectors, scalars, and tensors above ADS5 times S5. These dots here correspond to representations of the rotation group of S5 SO6. Turns out that these gentlemen, for this particular example, kind of overworked, because the problem can be solved using other techniques, particularly for a maximally symmetric situation as ADS5 times S5. The problem is completely solved by group theory. ADS 5 times 5 is also homogeneous, which means that there are available techniques available for cosec spaces that work in that type of situation as well. So it turns out that they actually didn't need to go through the hard way in order to get the spectral property to another step. So, well, I just mentioned this, that it's actually essentially for type ADS 5 times S5 or ADS 4 times S7. The problem can be solved just using group theory because all the multiplets are short and the dimensions are fixed by the odd charges. But the situations with less than maximal supersymmetry, there'll be long multiplets in the spectra as well, and then you do need to resort to other techniques to get those dimensions as well. In the homogeneous situation, there's algebraic techniques that you can employ, and I bring this up because the techniques I'm going to introduce today sort of generalize this picture. In general, though, in a generic situation, you're on your own, and you do need to resort to the hard way that Newman-Huygens et al. Used to compute the spectrum, because you'll have fluxes, you'll have inhomogeneous metrics, and none of those techniques shortcuts will apply to those situations. All right, so as the bottom line for the new techniques that I'll present today is that for certain de Sitter solutions, those that arise by consistent uplift, that have some consistent truncation associated to them, it is possible to construct the complete Kaluza-Klein spectrum using a combination of group theory techniques and new techniques based on so-called exceptional field theory. That the group theory still gives the complete algebraic structure of the spectrum, and particularly the short multiplets as well fixed at this step. But the long multiplets need to be computed, and exceptional field theory is very helpful in order to do that. Another way of thinking of these new techniques is the following. This is again taken from Kim Roman's Newman-Huygens, and the red dots here at the bottom of the lines correspond to the modes that fill out that particular consistently truncated supergravity. At that level, at the gate supergravity level, you can compute these masses, and then the exceptional field theory story would let you figure out what the dots at the Kaluza-Klein tower are. So you gain that you use the exceptional formalism to figure out the higher dots in the towers from the bottom.
In the towers, you mean on the lines, or
say it again?
along the lines that are drawn, or just going vertical?
Oh no, along these lines, yeah.
So there are some lines.
No, these lines are a little schematic, so you just do this Kaluza-Klein level by Kaluza-Klein level as opposed to it'll become clear as we go along. All right, so there's of course this exceptional field theory story is big, and I won't cover it in much more detail as needed as to just discuss the features I need to motivate that formula for this particular situation. And in some sense, this is related to the existence of consistent truncations, not necessarily though. But since I mentioned that one of the key ingredients I need in my formalism is the existence of such consistent uplift, let me remind you that by this expression, I mean that if I have two theories, one high dimensional, one lower dimensional, both of them are related by a consistent truncation if the solutions of the lower dimensional theory give rise to solutions upstairs as well. And these situations, these pairs of theories are quite scarce, and one of them is precisely type 2b on S5. Related to the Newman-Huygens story, even though of course he didn't use any of these formulas. Okay, that gives me rise to discuss the field content of lower dimensional gauge supergravity. So let me start, for example, with a 4-dimensional situation. And it turns out that the fields, I'll just go through this equals 4 and equals 8 case as way of example, but I could have covered the 5D situation as well. Turns out that the fields in this lower dimensional supergravity fill out representations of the exceptional group C7 in the 4-dimensional situation. That's for the bosons, or the maximally compact case, SU8 in this case for the fermions. Okay, and all these fields come in what I described by a Lagrangian that codifies the interactions, and in particular, there's a scalar potential with the 70 scalars in the model that takes on this form. M is the coset, essentially the coset representative of E7 on SU8, and X is our constant matrices that go by the name of the embedding tensor. Anyways, the 11-dimensional field content, for example, is very different. So you got a metric and you got a 3-fold, but consider that for some reason, you split the 11D coordinates as a 4+7 split. And then you expand your fields according to that splitting in this way, and then start looking more 4-dimensional, even though this is just a mere rewriting, perhaps slightly baroque or complicated, of the theory, because you're not truncating anything. You're just giving all the fields and you're just giving all the dimensions. Okay? All you're doing is just you are splitting your space-time like this. When you start collecting these fields, for example, let's focus on the vectors, things like just have Lorentz external index here. Turns out that all these building blocks can be combined into a single object using just some group theory, if you like. These identifications are not straightforward because in order for these fields to transform correctly under diffeomorphism, you still need to redefine these fields accordingly together with some combinations of these guys. In any case, if you start doing that, what you gain is that your high dimensional supergravities look like that four-dimensional counterparts. So this exceptional field theory story is just a reformulation of the high dimensional supergravities that kind of make them look, say, 4-dimensional. One of the things that you need to do is to expand your space-time accordingly to 56 extra dimensions. That's a tall in a bay. But there's so-called section conditions that select the relevant dimensions out of those extra dimensions. All right. Point though is that all these fields that are entirely still 11-dimensional because I haven't done any truncation. They still describe by Lagrangian that as the field content itself resembles the 4D Lagrangian, but it's still 11-dimensional. How can you make contact between the two descriptions? Well, you can consistently truncate if you like. And when you do that, you are extracting the four-dimensional fields consistently with the high-dimensional equations of motion, provided these so-called Sheck-Schwarz matrices satisfy some condition in terms of some lead derivative that you define on your extended internal dimensions. These matrices that appear here in the consistent truncation conditions just reappear in the four-dimensional theory as the constants that quantify the interactions downstairs. That is as the embedding tensor. Okay, so
so this is supposed to be also an explanation for why the consistent truncation exists.
Yes, now it's very well understood that all consistent truncations, the maximal that don't break supersymmetry, are of this type, are generalized Schwartz, and a consistent truncation exists if and only if these equations are satisfied with constant x's.
Kind of more intuitive. Is there a more intuitive understanding of why they exist? This looks a bit abstract to me.
It is a bit abstract, but this condition here is telling you that there's a geometrical way of formulating this exceptional field theory story that is very geometrical, and that goes under the name of exceptional generalized geometry. In those cases, these U's, in that more geometric language, these you can regard as a Vielbein of E7 over SU8, and there's a metric associated to that, which is the square of that Vielbein. And if this is the condition for the Vielbein to be globally defined in that extended space, in other words, to behave as a group manifold. So the geometric intuition behind these conditions is that you are creating a parallelization, you are trivializing the internal space. It's just a thumbs from this point of view. More precisely, it's a group manifold from this point of view. So that's perhaps the more intuitive explanation, or the more intuitive picture. All right, so having at this point, what I've done is
maybe I'll interrupt again. So
yeah, of course.
Can you view it as saying that you keep all the fields that are invariant under certain symmetry, for example? You take, so for example, for the case of the reduction on the torus, you take the 11-dimensional field that are invariant. Is there something that is conceptually similar? What you're discussing is that conceptually similar to that, but with
it's it's conceptually similar to that, but I don't think that there's no. I don't think there's an intuition along those lines. If there is a symmetry, though, if there is a symmetry in the conventional sense, you can always write equations like this. But the other way around is not so intuitive. All right, so bottom line until now is I've related the two nonlinear theories, upstairs and downstairs, via this Schwartz reduction. And one of the headlines I announced at the beginning of the talk is that I'm going to use the spectral problem downstairs to kind of generate the spectral problem all the way up. So let me review the spectral problem downstairs first in a couple of slides. But for that, I first need to focus on a particular vacuum, because recall that we're dealing with theories that have scalar potentials, and those scalar potentials may be extremized and may give rise to different vacuum. So the fact that I'm sort of thinking of a main kind of maximally symmetry and symmetry preserving vacuum, as in ADS 5 times S5, doesn't mean that I need to confine myself to that particular situation. And I can use this formalism to construct the spectra associated to fluctuations about different vacua of that scalar potential. So you may be wondering, what is the vacuum structure of that scalar potential? And people have only recently figured out that that the number of vacua in those models is typically of order 100. Most of them are non-supersymmetric. The most interesting ones are perhaps the supersymmetric ones, and those are very, very limited. So those are the vacua we're talking about. And I'll be more explicit about perhaps these two n equals 2 examples in 11D and in type 2A.
Are the non-supersymmetric ones stable, or can you say that with your method?
The non-supersymmetric ones, most of them are unstable already at this level and already at the gauge supergravity level. Some of them don't preserve instabilities at the gauge supergravity level, but the Kaluza-Klein tower does preserve some instabilities. And some of them, the ones in the type 2A picture, they're stable at the supergravity level.
So that's in this other massive supergravity.
In the massive 2A.
That's the only case where you have stable.
If the non-supersymmetric ones or some non-supersymmetric ones are stable they don't have instabilities in the Kaluza-Klein tower.
Is that the manifold with all? Is it completely smooth in the internal dimensions, or does it have some brains?
No, everything's smooth here.
Okay.
Everything's smooth. There's no singularities whatsoever in the internal space. I'll be showing particular examples corresponding to these two cases, n equals 2 cases, because they're just okay, so again, at the lower dimensional level, you can figure out the spectrum just at that slice. That's very limited, but let me focus on that for the moment. And you can look at the algebraic structure of the spectrum, and for that you can just use group theory, because it turns out that the algebraic structure of the spectrum at the central SOA point is known. And if there's any, actually there are other critical points of the scalar potential that preserve a subgroup G of SOA, and it turns out that the corresponding modes are just lie in the representations that appear in the branching of SOA under G. And of course, those individual states need to group up into supermultiplexes versus supersymmetry preserved, and that's an extra ingredient. How do you compute the actual masses? Well, there's mass matrices in the supergravity literature that you can just resort to and diagonalize. So that you're done. And then if you do that, then you get precisely this red dot. How do you generate the full tower? Look at the exceptional field theory story of or look at the XFT side of things. And the new methods are very helpful, because if we go back to Nieuwenhuizen's steps, these gauge redundancies are already built in the formalism, so you don't need to deal with that anymore. So that's kind of that's nice, because you get that mileage. You still need to, of course, linearize the equations of motion of the exceptional field theory. But another interesting aspect, which is extremely helpful, is that you do not need to expand in different harmonics of the different Laplacians of the internal space. You just need to expand in scalars, which is a dramatic simplification. Of course, you still get mass matrices that you need to diagonalize in order to get eigenvalues. But these 2 points, the gauge redundancy thing and the expansion in scalars, is what is the actual game changer in these situations. Why is this? Because it turns out that at the full nonlinear level already, the supergravity fields that you can see on the right-hand sides are in fact scalars, or with respect to the E7 symmetry. That's a way of seeing that, and for that reason, we can just expand those fields in terms of spherical harmonics, scalar spherical harmonics, and we expand the whole lot of them in spherical harmonics without involving any other harmonics of other types. There's another justification for this step. Lambda here, just know that lambda here, this index is lambda, just label the symmetric traceless polynomials on the corresponding spheres. There's another intuition behind this step, which was given by Engels and Nikolai long ago, which is that the full tower of Kaluza-Klein modes in for the front group in SOA situation corresponds to the tensor product of the supergravity multiplet and the symmetric traceless representation of SOA. And here is the Kaluza-Klein level. So at n=0, I recover gauge supergravity. So that's why I'm always identifying implicitly gauge supergravity as the n=0 slice. At other ends, parameterize the tower, the Kaluza-Klein tower. This is valid at the SOA point. But again, if I consider a different solution with less symmetry, I simply go through the group theory and branch the representations under G. And if on top of that, if I have supersymmetry, then I need to make sure that the corresponding states arrange themselves into. That's good as far as the algebraic structure is concerned. How do I compute the actual masses? Well, the actual masses, I linearize the exceptional field theory field equations, and I obtain mass matrices, infinite dimensional mass matrices that reduce to the gauge supergravity counterparts that I showed earlier on, and have extra pieces corresponding to these T's, and these T's I showed here are just the SOA generators in these infinite dimensional representations. So that means that these are block diagonal matrices that I can diagonalize level by level. Okay, so a couple of noteworthy features here that in order to find the full spectrum, I'm literally extrapolating the gauge supergravity spectrum all the way up to the Kaluza-Klein towers. So I'm essentially doing a 4-dimensional calculation. I don't need to know the solution in full high-dimensional form. And the only remnant of the internal directions that appear in the calculation is this constant matrices that codify the SOA generators. Again, I mean, emphasize that supersymmetry doesn't play any significant role here. That can compute spectra, non-supersymmetric spectra as well. Okay, so what are a few examples of field theories where I can use this technology? I'm going to focus on, again, going back to the table, I'm going to focus on these two solutions in 11D and type 2A. This 11D solution was constructed by Varela, Hilton, Warner, and corresponds to essentially a mass deformation of ABJM. More generally, turns out that ABJM admits two deformations, or two types of deformations that preserve SU3 flavor. One of them is quadratic, the other one is cubic. Towards the end of the talk, I'll address the cubic situation for now. This Harada-Pilz-Warner situation corresponds to that mass deformation, and at the level of the Lagrangian, that leads to mass terms in the 35E and 35C of that split from 35E and 35C of SOA, which correspond to gauge supergravity scalars. And for that reason, this flow, or more precisely the endpoint, the low energy endpoint of this flow is described by d=4 supergravity. And we have computed the spectrum using these techniques. Another type of situation where you can use these techniques correspond to solutions that have type 2A duals, and those are those are constructed on the boundary side by decorating young males with Chern-Simons terms. And of course, in 3D, the gauge coupling is irrelevant, and at low energies, Chern-Simons term dominate. And you can further decorate this with extra supersymmetric couplings, as was done by Schwartz pre-APJM. And while these, most of these field theories don't have gravity duals, some of them do have duals in type 2A. For example, that n equals 2 point that I showed before correspond to Chern-Simons SUN gauge fields coupled to 3 chirals with an SU3 flavor that rotates these, and that have a superpotential of this form. In fact, this model is precisely an analog, a direct analog of n equals 4 young males with an area n equals 1 language. The gravity dual is an ADS4 times S4, where going back to Juan's question, that geometry is smooth and looks like that. It just want to show it, not because we're going to need it, but just to give you the idea that we're actually computing the spectrum, the Kaluza-Klein spectrum, associated to this configuration. And using traditional methods, I suppose, I was going to say there's no way, but that guess with a lot of pain, you could, I guess, compute that. So there's definitely a lot of mileage gained by these new techniques, because we compute the spectrum of this monster with these methods. And we've got a bunch of results here. We compute the gravitron spectrum. We compute the short spectrum. We didn't need all that stuff for the short spectrum, because this follows from group theory. We can wonder, how many scalars do we have that are relevant or classically marginal? And we can list all of them. We can find dimensions for the formulae that follow a very nice pattern in terms of SU3 related quantities and hard charge NDR charges. And more generally, for most of the solutions I showed, there is a general formula that for the dimensions of the conformal multiplets in the symmetric cases that follow in some simple way the charges or the preserved charges of the symmetries that the solutions have. Some of them, if the symmetry, if the residual symmetry is relatively high, follow this formula. For other solutions, there's no formula. And I don't have an intuition why that is not. But the characteristic polynomials of the matrices start to look more and more complicated as you go up in Kaluza-Klein levels. So this is general. This formula is general. It holds for some solutions with sufficiently high symmetry, but it's not universal because it doesn't hold for all of them. And I don't have an understanding why. All right, so that's good as far as this particular models is concerned. But even though I argue that these solutions that you can analyze, you can compute the spectrum of, arise by the hundreds, arguably these are not the most interesting solutions out there, and you'd like to extend these methods beyond the assumption that there should be a consistent truncation. So how do we, this is a little bit of work in progress, and I won't have much more to say, but what kind of extensions can you, what type of situations can you expect to address using these techniques? Well, perhaps the easiest one beyond the truncation situation is that where the expansions are still controlled by eigenfunctions of the scalar Laplacian on the internal space. And I'll give examples in a second, but these internal spaces typically will be spheres, but not necessarily. So the key point you want to keep is this type of decompositions where there's some sort of Schwartz reduction answers, but the algebra that relates these matrices is now such that these tensors are no longer constant, and they depend on the internal dimensions. So in these cases, what you find, or what you gain, is that you still know the algebraic structure of the spectrum, because it's still given in terms of products of spherical harmonics, if you like. But you don't get mass matrices. You need to integrate differential equations because these guys are not constant. Okay, so there's three types of situations where this holds. For example, the cubic deformation of ABJM, where that's still an internal space, which is of course a seventh sphere. But the reason why this is not amenable to this type of consistent truncation methods is that the associated modes lie outside the consistent truncation. So it turns out that this type of situation in the exceptional field theory language can be generated using some type of arrangement like this one. There'll be example on one that goes beyond the case I presented today. Example number two would be the beta deformations, or the marginal deformations of n equals 4 Young-Mills. Again, those deformations are generated at linear level by modes that lie outside the gauge supergravity, and therefore can't be constructed, or the spectrum above those conformal manifolds can't be assessed using the techniques I presented today. But again, they do conform to some sort of expression of this type. And a third example that you can look at is rat brains. And it's perhaps less trivial, because in these cases, it turns out you can still find exceptional field theory descriptions with the relevant matrices of, again, the same type. So these cases start probing these three type of situations, start probing the applicability of these techniques beyond the consistent truncation situation, and of course, more generally, would like to have a better grasp of these methods for more general background. So I suppose that's pretty much everything I wanted to say. So thanks for my.
Thank you.
So for flux complications, there are some examples where the spectrum comes out to be integer, even though there's no obvious reason for it. I mean, does that happen also in any of these cases?
No, the spectrum is not necessarily integer in these cases. If the solutions have sufficiently high symmetry, the dimensions do come are given by some square root of typically irrational numbers, but not necessarily. So in other cases where the symmetry is even more reduced, the conformal dimensions don't follow an obvious pattern.
So algebraic numbers?
No, not necessarily. No. I don't really understand why there's that distinction, because there's no obvious reason why that happens, as far as I can tell. Thanks for the question.
Is there any progress on using exceptional field theory for computing 3-point functions?
Yeah, that's a very good question, and I don't think there's nothing out there yet.
Do you think it's possible?
I think I think these techniques could be used for that. Yes, because I mean, you perhaps I'm not really sure how these methods would talk to, bootstrapping the calculation using, mailing transforms and things like that. But going back to the old-fashioned approach of computing the action until certain level, these methods are certainly useful.
Can you use these ideas, for example, to compute the wave equations and so on around the black hole background? For example, if you have a black hole, you might be interested in the quasi-normal modes of this black hole.
Yeah, I pointed out your recent paper. I'm not sure, and it's not obvious how do you do that. If these methods will give you any mileage in integrating the wave equation on those backgrounds.
Or maybe not integrating, but just get to the wave equations. Just
Okay,
the same type of algebra that you're doing here. I guess, yeah, another background that might be interesting to understand the spectrum around maybe the ADS2 black hole so the black hole, supersymmetric black hole in ADS 5 times S5. So it has an ADS2 near horizon region spectrum. For example, for something like that, is there
for something like that, that would be,
it is a solution of gauge.
yes, that would be, I think that there would be these methods could be applied in that case. But are you saying that for some modification of those methods could be amenable to computing that spectrum? But are you saying that would you be identifying the spectrum above the antenna theta near horizon with the quasi-normal modes? That's not.
Well, they are related, but in principle, these are two different questions. They are the quasi-normal modes of the near extreme. That's because of the SL2 symmetry.
Whether the whether the spectrum is related to the quasi-normal mode spectrum.
Well, in ADS2, it's related because of SL2 symmetry. So that relation we know already. But I guess if you found the spectrum.
The spectrum could in principle be found using these methods.
Yeah, I don't know if I don't know whether from the quantum mechanical side we have a prediction.
I'm not sure of that. I mean, from the classical point of view, the reason here for this particular presentation stopped in 4D is that if you go lower than that, then all these duality groups, all these global symmetry groups start becoming infinite. And then when dealing with that situation, it starts, you have to think a little bit more. But in principle, I don't see why that couldn't be done.
Another question?
Is there any hope of using these methods also for solutions with brains? I mean, if the Potensky stress or
That's so these tiny steps we're taking towards generalizing these methods for cases that are beyond what I just said today, perhaps give us some intuition of what the actual full-blown generalization would be. But for the moment, I'd be cautious. But In principle, yes. So there's two main things that these methods do to bypass, the general pain of the usual method, which is the gauge fixing process, and then the expansion in harmonics. The gauge fixing process, this exceptional field theory story, is going to have it built in no matter what. So you're going to have that always. So that's good, for the generic situation. The expansion, though, it's very special. So the fact that I can expand in only scalars, scalar harmonics, eigenfunctions of the scalar Laplacian, is what I can do right now. Or is, it simplifies the situation, but in general, a more general flux background won't be of that type.
There are no more questions. The time was carrying.